Hello everyone. Under the topic of power system analysis and equal area criteria, in this video, I'd like to talk about what happens following a fault. So, stability under temporary fault. So, what do I mean by temporary fault? Is there is a fault for a small time duration, after which the fault is cleared, and then we are asking the question: is the synchronous machine maintaining stability or not? So let me explain it further with a diagram. So this is the mechanical power input given to the synchronous machine, and I am generating some EMF inside that, and then there is, although I am showing it outside, this is the internal impedance of the synchronous machine. So let's denote it as by Jx. And then this EG, you can think of having some delta naught as the initial angle. And imagine this as your reference bus V at an angle of delta, which I'll assume to be 1 at an angle of 0 degrees. Now, there is a fault here on this bus. So, when the fault is not happening, then some electrical power PE is entering into the grid. So PM mechanical power is entering into the machine, and then here for simplicity, I have not considered any electrical losses because of the resistance and so on. So PM and PE will be equal, and then the power is being transferred here. Now momentarily there is a fault, and when there is a fault the voltage will become zero because this is a voltage three-phase fault and this is a ground voltage zero, so this voltage will become zero, and as a result the electrical power will become zero. Now we also know that the expression for PE is Eg into V by X sine of delta. So the whatever is the delta at this stage, the delta of the machine is delta naught. At t equal to 0, delta is delta naught as shown in this figure. But in general, this is the electrical power, and this quantity we are denoting as P max sine delta. So if I draw it as a plot, so it will be some curve like this. So let me draw a bigger figure. So this is PE, which is nothing but P max sine delta. And P max is determined by whatever is EG value, V, X, and so on. So P max is actually EG V by X. Now, how much mechanical power being input? It's all under our control because this is a infinite bus, and then I'm just generating power and injecting into the bus. So depending on your prime mover, depending on amount of power produced by the prime mover, for example, if it is steam turbine, depending on the amount of steam, amount of PM will be defined. So let's let's say this line represents your PM, which is there, and this x-axis is actually delta, and y-axis is our powers being generated. For stable operation, so we also know the swing equation. So the swing equation is 2 h by omega d square delta by dt square is equal to Pm minus Pe. This is all in per unit. So we had derived this some other time. So for now, take this as the swing equation. So if Pm is more and Pe is less, then the rotor will accelerate. So this delta is the rotor angle, rotor angle with reference to the moving rotating reference frame. If Pe is more than Pm, so this is denoted as Pa. So where Pa is accelerating power. So if as the name says, if Pa is positive, PM mechanical power is more than the electrical power, then the rotor will accelerate. Otherwise, the rotor will decelerate. So now so we are operating at this point actually because PM is equal to PE and this is a stable point, this is unstable point. So at this point PM equal to PE and then we are operating at time t equal to 0. So here the delta naught is the uh, present steady state angle. Now under these conditions fault has occurred and when the fault has occurred, so let me write it here. At t equal to 0 and before that, uh, delta equal to delta naught and then PM equal to PE and then we are operating at stable, operating stable point. Now at t equal to 0 plus, that means just after t equal to 0, immediately, that means that is where we are saying fault occurs. Fault occurs on generator bus. So that is three-phase bolted fault, symmetrical. Bolted fault means the fault impedance is 0. When that occurs, then the entire this PE will become 0 and then we have this is nothing but PM minus 0. So accelerating power is there, the delta will increase. What if the fault is not cleared? So if the fault is not cleared, of course the motor will keeps on, the generator will keep on accelerating and eventually it will lose synchronism and it is not stable. That is not the case. What we are now looking at is at t equal to t1, the fault is cleared. So after a time t equal to t1, the fault is cleared. The question we are asking is the machine stable? Is the generator stable? So there is here at this point I would like to define TC. TC is the critical clearing time. Therefore, if the fault has to be cleared before that time. So therefore, if T1 is greater than TC, then unstable. If T1 is equal to TC, that is critically stable, and then if T1 is less than TC, then it is stable. Therefore, it is very important to clear the fault before this critical clearing time so that I am able to maintain the stability of the system. So, how is the fault cleared? So, we sense the fault current, so there will be a relay here which sends the fault current, and there might be a circuit breaker here which disconnects the generator and so on, that kind of thing. So let's come back to the situation here now. So what I have done is at t equal to 0 fault is created and at t equal to t1 fault is cleared. Now at time t equal to t1, when the fault is cleared, we know that the rotor is accelerating. So therefore let's say this is the place, this is the position where the rotor, the fault has been cleared, so I get this angle as delta 1. So now what about this area? So at this point PM equal to PE, but after this electrical power actually is nothing but your x-axis and mechanical power input is y-axis. So this much of variation is there. This much of power is being submitted to the rotor. So therefore this area A1 is kind of proportional to the total energy. So this is accelerating energy. So the rotor is accelerating. That's why I am increasing from delta 0 to delta 1. And at this point, already since I am in acceleration, I am rotating at a super synchronous speed. So even though the fault is cleared, the delta angle will keep increasing, and it will reach to a point which is delta max. But then at delta 1 itself, the electrical power is going to come back because the fault has been cleared. So at this point, electrical power is greater than mechanical power. So for example, you see here electric power is here, mechanical power is only this much. So during the duration of the fault, we are assuming mechanical power is always constant, because in that short few milliseconds time, not much of variation will be there in the mechanical input to the machine. So, since the PE is more than PM, the accelerating power is negative. That means the motor is actually decelerating. So, therefore, it cannot go on forever. There will be some maximum point it will reach, and then after reaching that maximum point, the machine will come back to its original point here after a few oscillations, assuming that the oscillations are going to be damped because of some friction or some losses and so on. Now, so this area will be A2. So the concept here is how much this area A2 can be. So basically this is the energy stored in the rotating mass. That much energy has to be taken out. So equal amount of A2 area will be there such that the energy is taken out of the machine, and finally it will swing and then come back to delta naught. So the question is whether this much area is allowed here or not, available here or not, and to that extent the rotor will overswing and go up to delta max. So this is the equal area criteria. So if A2 equal to A1, then machine will come back to stability. Machine will be stable. All this happened because of this this delta 1 I have cleared here. So sometimes if I make a delay in clearing the fault, so I'll show you in another diagram. So let's do this. So I have this as PE, and then this as PM, and this is delta naught. Now, instead of clearing it very early, delta 1, let's say I make some delay. I take long time to clear the fault at this point. So then this much of energy is actually stored in the rotating mass, which results in increase of the acceleration of the machine. Now, how to get back that energy? So at this point, delta 1, I had cleared the fault. At this point, delta 1, I had cleared the fault. So therefore, after clearing the fault, P is coming back, P is more than there, this deceleration is going on. But then I cannot get more area. So the area A2 is actually less than area A1 because I made too much delay in clearing the fault. So because of this, since area is less than A2, the deceleration area is less, acceleration area is more. So machine going on accelerating, and therefore it will lose the stability. So machine loses stability. I say generator loses stability. So there is a particular point that, as I mentioned, critical clearing point when the machine will remain stable. So if I now draw that, so this would be the critical clearing. So this maximum allowed value for delta is that, and this is delta naught. So one thing you should notice here, this is 0, this is pi, and this is the value of delta. So delta naught is nothing but pi minus, sorry, delta max is nothing but pi minus delta naught. So this will be later useful. So this gap is equal to this gap because these are coming out same PM here and here. But that is not the point here. The point is the critical clearing. Let me just approximately do that. Let's say there is some particular angle, critical clearing angle. Just a minute. So some critical angle that I would like to find out. So that is what I am going to do in the next video. So such that A1 is equal to A2. What is the delta C? So this delta C is right now unknown. In the next video, we are going to find what is the delta C. Thank you. So hello everyone. So I started off explaining stability under temporary fault, and this is just a continuation video. So far what we have discussed is that in the final case, when area A1 is equal to area A2, so that is the critical case where I have to clear the, so this is the critical clearing angle. So delta C is critical clearing angle, and associated with critical clearing angle will be critical clearing time, TC. So critical clearing time. So these two quantities I would like to find out. So this is the video for doing that. So in the rest of this I'll do that. So let's take a fresh sheet. So the problem is like this. So the problem is, so this is PM and this is PE, and currently I'm operating at delta naught at time t equal to 0, and then there is a fault, and then the fault is cleared, and up at sometime here somewhere delta C. So this is a critical clearing angle. So at this angle, so this, as you know, this is angle in delta in pi. So up to here it is pi. So this is the rotor angle, and then this is the power. So at this point I'll have delta max, and then we are looking for a condition where this area is equal to this area. So mathematically I want to find out, given delta naught, what is delta C such that these two areas are equal. So the expression P is P max sine delta. There is just a sine, and then the amplitude is P max somewhere here. So it is not that difficult. We can do it simple derivation to find what is this delta C. So let's do that. What I want to do is just what is A1. So A1 is nothing but this rectangular box. So therefore the area of A1 will be nothing but PM into delta C minus delta naught. So this just gives me the area of A1. I can also integrate PM from delta naught to delta C, which actually comes out to be the same thing. This is area A1. What is area A2? So area A2 basically is that if I give some markings, let's call this A, B, C, D, and let's call this E and F. So the total area, that is E, C, D, F, will be the integration of this P, and minus this PM will be the that area. So if I just integrate uh, delta C to delta max, the PE minus PM. If I integrate this, uh, that will be the area A2 with respect to d delta, of course. So I want to do this now. So and we have all this. So P anyway, this area 2 would be negative if you are actually going as per the this one, uh, that is as per the expression of swing equation. But then here I am just wanting to calculate A2, and then I will equate these two areas. Then I will get the equal area criteria. So what is so from delta C to delta max, I want to integrate. So this curve, that is PE, minus this curve, that is PM. So I get something like this. So P is P max sine delta minus PM. That's all with respect to d delta. Now, what is integration of this? Integration of sine is minus cos delta, and then P max is anyway constant, that is just a coefficient. So this is delta C to delta max. Similarly, what is integration of PM d delta is nothing but PM into delta, and the delta range is delta C to delta max. Now if I substitute it once again, so P max multiplied by, so I'll get the higher limit minus smaller limit, but then since minus sign is there, so it will be cos delta C minus cos delta max. So I think this is just a basic substitution. So minus PM into delta max minus delta C. So this whole thing is area 2. Now if I look at what is A1, so A1, and if I want to equate this to A2, so A1 is here, PM delta C minus delta naught. So from these two, I can actually cancel out this term. PM minus delta C will be plus, and both sides this will be cancelled out. And then I'll get PM delta naught equal to this one, P max cos delta C minus cos delta max. So here this term is cancelled, so minus PM delta max. So just bear with me, we are almost at the end. So this is unknown, sorry, this is known, this is known, this is known, this is known, and this also known. Only thing that is unknown is delta C. So just I want to write in terms of delta C. So what I get, so this term will go to the other side. So PM delta max minus delta naught, and then it gets divided by P max, and from this will get added. So all of that will be equal to cos of delta C. So everything on the right hand side is known. So just by doing this calculation, I will be able to find out what it is, what the delta C is. So finally delta C is cos inverse of all of this. So this is formula for critical clearing angle. Now just a little bit of more thing is there. Now that you know delta C, I want to find out what is the critical clearing time. So I know delta C, at what time the delta C angle will come, so that I can, before that time I can clear the fault. So for that we need to again go back to the swing equation. So the swing equation is something like this. That is 2h by omega b, or 2h by omega, and this is d delta d square delta by dt square equal to pm minus pe. But during the fault pe is absent, so I'll take p is 0, so I'll just remove that. From this I want to find out what is delta c. So in fact delta c is known. At what time does delta c occur, I want to find out. So just do some manipulation. So the second derivative of delta is nothing but omega pm by 2h. So from this integrating, so I get integrating with respect to time d delta by dt. So second derivative will become first derivative, and this will simply be multiplied by time. So integrating on both sides, this one. By integrating, I get this. There is no constant of integration because this second derivative is actually with respect to stationary, with respect to rotating reference frame. So at this stage, there is no constant term, or the constant term is actually 0 in this case. Now again if I derive this, so again I'll get delta equal to again once again derivation of this. So Pm, this will remain as it is. So it will be t square by 2. The integration of t is t square by 2 plus some delta naught, the initial value of delta. So why here the constant is not there is since d delta naught by dt is equal to 0. So at steady state condition, there is no change in the delta naught, or this is constant actually. Anyway, so let's continue. Now in this, if I substitute delta c, then I'll get Tc, and delta c is known from the previous case. Now I will find what is Tc. So Tc is like this. So first delta c minus delta naught will be there, and then to that I will multiply 4h and divide by omega pm, and then square root I will apply. So this is what will give me the value of critical clearing time. So we have, in this video we had critical clearing angle formula, and then we have the formula for critical clearing time. All of this is based on this particular concept that I have explained. So let's do one example problem on this maybe in the next video, and then we'll get more understanding of how to use this.